Alright, so we have a loaf of bread pushing a jar of peanut butter and a jar of jelly, and there's 65 kilograms of peanut butter, we got 28 kilograms of jelly, and they're accelerating at 1.8. And we're going to find out a few things about the situation. So let's just start simple. Let's find out how much the bread is pushing with. Now, to take this nice and simple, we will say that there is no friction right now whatsoever, so there's no friction to worry about. So what is the applied force from the bread? Well, if there's no friction really, there's only him trying to speed things up, there's nothing slowing it down. So his applied force would also be the net force because there's nothing else going on. So the net force, of course, is just NA, and we would combine the two masses together, multiply them by the acceleration, and we have a net force of 167 newtons, which would also be how much he is pushing with because there's no friction or anything slowing it down. Okay, so what if we change the situation a little bit? Okay, so what if we changed it? So now we said that the acceleration is only 0.5 meters per second squared. So what is the force of friction? Well, the applied force is still 167. So he's pushing with 167 newtons. That is my applied force. My net force isn't going to be the same thing anymore. If I do my net force, F equals ma, with my new acceleration, I get a force of, give or take a little bit, around 47 newtons. So let's see, I've got 167 trying to move it. I'm only getting 47, so I'm losing 120 newtons. Okay, so I must be losing 120 newtons to the force of friction. Okay, well, let's find another force. Let's find out the normal force. What's the normal force between the peanut butter and the ground? Alright, so what's the normal force between the peanut butter and the ground? Well, the only reason there's normal force between the peanut butter and the ground is because gravity is pulling the peanut butter down. The bread has nothing to do with it. The jelly has nothing to do with it. Neither the bread or the jelly are pushing the peanut butter down into the ground. The only thing pushing the peanut butter into the ground is the force of gravity. So if we would do mg for the peanut butter, we can actually calculate how much normal force there is. So if I do the 65 times 9.81, the weight of the peanut butter is 638 newtons. So that's how much gravity is pulling down on the peanut butter, so that must be how much the normal force or the natural force is pushing back up. So this would also be equal to the normal force. So the normal force would be 638 newtons going straight up. So since I've incorporated friction here, maybe we want to try and find out what the coefficient of friction is. Now, we don't just have one source of friction, we have two sources of friction. Both of them have friction. We'll just say it's the same coefficient for each. Now, to find the coefficient of friction, we need the force of friction as well as Fn. Now, we know the Fn for the peanut butter is 638 because that was the weight of the peanut butter. So for this guy, the Fn is 638. Well, the same type of calculation can be done for the jelly. So if we find the weight of the jelly, if we do the mg for the jelly, that is 275 newtons, and that would be the Fn for the jelly. So using their weights, the weight of the peanut butter is 638 going down, Fn's up 638. Mg, or weight of the jelly, is 275 going down, the Fn for the jelly is just going to be 275 going up. And since we're just going to use the same coefficient of friction for both of them, we can actually just use the total Fn over here because really when they're sort of side by side on the same surface, same coefficient, they're almost sort of like one object. So you could do them separately if you wanted to, but we're just going to do them together just to make things a little easier. So I know my force of friction was 120. So if I do my Fn, I put my Fn's together. So I'll add the 638 and 275 for a total normal force of about 913 newtons. So if I take my force friction of 120 and I divide it by the 913, I get a coefficient of about 0.13. Again, you could just done the friction separately for each one. I just sort of treated them as one gigantic mass since they're on the same surface, same coefficient and all that kind of stuff. Yeah, it just made it a little bit easier that way. And the coefficient would be 0.13.